Hi, it's Andrew here, and as you know, Fred and I are taking a little break at the moment while Fred swans around the Arctic. We'll be back with the first episode of Space Nuts for 2020 very soon. In the meantime, though, we thought you might like to take a listen to this episode of the new Dark Skies Conversations podcast coming soon. It features an interview with Fred. It's a great little background as to who he is and what he does. I know you've been listening to him for a few years, but people ask a lot of questions of Fred and his background. So just what does an astronomer-at-large do? You'll find out in this interview, and of course you can subscribe to Dark Skies Conversations wherever you get your podcasts from. So sit back, relax, and enjoy an interview with Fred on our Space Nuts platform, and keep an eye out for the Dark Skies Conversations podcast. And I'll chat to you again real soon on Space Nuts.
Hi, with a flick of a switch, we turn night to day and day to night. We can change seasons, actions, and states of mind. Light is everywhere, used endlessly and very much a part of our modern world. But what is it? How do we use it? And how is it changing our environment and our behaviours? A star-filled sky used to be our evening's entertainment. Now it's Netflix, iPads, or even a podcast. When was the last time you looked at the night sky? I'm Marnie Ogg, and this is Dark Sky Conversations, the podcast that brings people and science together to shed light. With me today is Australia's Astronomer-at-Large, Professor Fred Watson, an astronomer, a science communicator working with the Department of Industry, Innovation and Science. Prior to this outlandish role, Fred was the astronomer in charge of the Anglo-Australian Telescope at Siding Spring Observatory, Australia's largest optical telescope. Fred is known for his award-winning books, Stargazer, The Life and Times of the Telescope, Why is Uranus Upside Down, and Star Craving Mad. He's also had 19 years of interviews on the ABC radio, TV and public appearances, and is now heading up some tours around the world with Fred Watson Tours. He's most recently well known for his podcast series, Space Nuts. Fred is well loved by the amateur astronomical community, but few know of his pioneering work on multi-object spectroscopy or his fascination for optics and binoculars. His all-round knowledge of all things light place him well as my first guest on Dark Sky Conversations. Thanks for joining us, Fred.
Thank you for having me. It's a pleasure to be here.
Thank you. So a question has to be asked. What does an astronomer-at-large actually do?
Hopes nobody will find out. No, so the job is essentially an outreach, education and advocacy role. It's all about trying to spread the word that science is good for people, to let the wider public know just what an enormous contribution Australia makes to the world of astronomy, and to engage with the wider community internationally. So there is now a lot of international involvement in astronomy.
With things like the Space Agency and...
The Space Agency, the fact that we are, Australia now has a strategic partnership with the European Southern Observatory, which operates the biggest telescopes in the world on the finest observatory site in the world in northern Chile. Right.
And so why is astronomy moving offshore to Chile, for example?
It's a really interesting story, and depends on how long you've got, but the story goes back to the 1960s, when astronomers realised that because of the advent of wide-bodied jets and cheap air flight, relatively cheap air flight, they could put their telescopes where the conditions were best rather than where the astronomers happened to be. Before that, observatories were always in cities because that's where astronomers lived. So there was a worldwide push to find the very best observing sites in the world during the 1960s. And that means sites that are dark without light pollution. That's, of course, a given to start with, which we might talk a bit more about, I guess. But also... sites which have clear weather, and in particular sites which have very stable atmospheres, a low level of atmospheric turbulence. And so sites were identified all over the world. Here in Australia, Siding Spring Mountain was discovered to be probably one of the best places to do astronomy or visible light astronomy in Australia. But we now know that some of the other sites in the world are even better. And in particular, it turns out that you need a place on a mountaintop, maybe 3,500 meters, that's kind of 13,000 feet, on the western seaboard of a continent. That's what you need to get this spectacular atmospheric stability. And the problem is we don't have that in Australia. We don't have a mountain that high on the western seaboard. I mean, we should perhaps pay somebody to build one if we could, but we can't do that. And so observatories elsewhere have better sites, and that's what's happened. The astronomical infrastructure has concentrated on those sites, principally in the southern hemisphere in northern Chile. In the northern hemisphere, it's principally the big island of Hawaii, which has the best conditions in the world. So that's why we engage with international facilities. Yeah.
So you mentioned there a couple of times light. The first being that light is... we moved away from light pollution. So what does that mean to an astronomer? What is light pollution, and why did you have to move away from it?
So many people don't realise that the night sky itself has its own luminosity, which comes partly from atoms in the upper atmosphere of the Earth relaxing after a hard day in the sun. They get excited and they release that radiation after dark. There's also dust in the solar system, which lights up the night sky, and a very faint background of stars and galaxies. They all contribute to a natural sky brightness. So astronomers are always battling against that. And often what they're doing is studying faint objects whose light is only maybe 1% brighter than this natural background. So they're right down there up against what nature throws at you. If you then put in artificial light, you lose the signal altogether. It's as simple as that. So you simply cannot tolerate any artificial light pollution for this kind of groundbreaking research.
And so are there technologies or anything that we can use to try and adapt these conditions, or is it just simply that we have to have no light pollution?
Yes,
both.
It really is. It really is that you can't have light pollution. The problem is astronomers look across what we call the whole visible waveband. So their measurements are made in all colours of light, from deep violet and beyond in what we call the ultraviolet, right up the wavelength scale to red light and infrared light and far infrared light. That's what you might say covers the visible light waveband. And light pollution tends to occupy much of that spectrum. For a while, there was an enthusiasm among astronomers for what are called low-pressure sodium vapor lamps. Because,
street lights.
Yeah, particularly for street lighting, because they emit light effectively of one single wavelength. It's orange light. It's very familiar to people.
Yes, and so you could eradicate that?
Yeah.
Okay.
So what that's doing is only polluting that one little bit of the spectrum, and the rest of the spectrum is much, much clearer. But you never get a city or a community that only has... So
everyone's outdoor housing lights, etc., etc.
Normal incandescent lights, mercury lights, all the rest of it. Actually, it turns out now, from the vantage point of 2019, that sodium vapor streetlights are almost obsolete, and that's for a number of reasons, operationally, for councils and bodies like that actually operate them. These sodium vapor lights have some disadvantages.
Right. Yeah. So I've heard you talk previously about a rainbow of light that you can study, and you've just mentioned then the band of light. Could you explain a little bit about the barcode of information that you get from this rainbow, this spectrum of colour that astronomers use?
So it's a really fascinating story. It goes back to Newton, who played around with a prism in the 1660s and discovered that you can shine white light, for example, sunlight, which is effectively white, even though it looks a bit yellowish to us. He could pass that light through a prism and break it up into this rainbow of colours, red, orange, yellow, green, blue and violet. Indigo isn't there. People used to say there was indigo in it as well, but it's not really there. So the six spectrum colours, which merge into one another. So it's actually a continuum. And it was Newton who coined the term spectrum, in fact.
Okay.
Back a little bit later than that, in the early 1800s, around 1802, a scientist by the name of Wollaston noticed that if he put sunlight through a prism and did it in a way that allowed you to look at specific wavelengths, look at specific colours. I shouldn't use that term because that came later. Wollaston noticed that there were dark lines crossing the spectrum of the sun. And he sort of thought, oh, this must be just where these colours all join together. But later in the 19th century, it was realised that those dark lines actually are the imprints of atoms in the atmosphere of the sun. And the positioning of the lines actually depends on which elements, which atomic elements are producing them. And so what you've got is this array of lines, and in the sun's case, it's tens of thousands of them. The early guys could only see, a handful, but now we recognise there are very many of them. And each one is the signature of a particular atom, particular element.
So
in the sun's
particular
atmosphere.
Element like hydrogen or
exactly.
helium.
The most common element is hydrogen, but we also find iron, calcium, sodium. All of those things are imprinted on the sun's spectrum. So if you use a device to form the spectrum, then you can tell with absolute clarity what the sun is made of.
So what is the device that you use?
It's called a spectrograph. Actually, in early days, it was called a spectroscope, which is just something for looking. That's the word scopus, at a spectrum. A spectroscope lets you look at a spectrum.
And the early days, when was this started?
The first people who really put spectroscopes together were at the turn of the 19th century. So the likes of Wollaston. So
it's been around for a while.
Yes, that's right. It was actually two German scientists by the name of Kirchhoff and Bunsen, a pair of them. They were the guys who really built the first decent spectroscope, and they were the people who worked out what was going on in the atmosphere of the sun. And it was actually an Englishman by the name of William Huggins, later Sir William Huggins, who tried that technique on the stars and realised that he could tell what the stars were made of.
Was there a comment that I remember somewhere that someone said that we would never know what all the stars...
It was, yes, that's right.
Yeah.
That was a Frenchman by the name of Auguste Comte, who was a philosopher. And in 1835, he wrote in a book, we'll never know what the stars are made of. We will never know their densities, their sizes. We just won't know their temperatures. He said, we'll never know these things. And actually, in that same year, a demonstration took place in Dublin, in fact, by a man called Charles Wheatstone, doing more or less the same as I was talking about with Wollaston. But he was using a metal... two pieces of metal with a spark passing between them, and he realised that if he looked at the spectrum of the spark, it told him what metal that the electrodes were made of. And that was, once again, building up to this idea. Kirchhoff and Bunsen were slightly later. They were around the 1860s.
So Comte got it wrong. We actually know a lot of stuff about the stars. Yeah.
He got it completely
So
wrong,
what other information does light give us about the universe?
It's hard to overestimate what we can learn about the spectrum of objects coming from the universe. So not only do you get, for example, if you're looking at stars, you not only get its composition, a star's composition, you can also tell whether it's moving towards or away from us and how fast it's moving.
And that's what you did with the radio velocity?
That's right. That's something called the radial velocity. It's the velocity along the line of sight. So measuring the velocity of a star towards or away from you is pretty straightforward to do with a spectrograph, although it actually took until the 1890s before another German called Karl Hermann
have this underhand, don't they?
Professor Vogel at Potsdam, he was the first guy to measure a radial velocity. So, yes, you can tell the speeds. Also, you can tell whether an object's rotating. You can see that from the spectrum. You can even tell whether it has a magnetic field, because a magnetic field actually splits up the spectrum lines that you see. But wait, there's more.
There's more, yeah.
There's more, because you can use, and this is technology that we really have we've only had for the last 24, 25 years. You can use a spectrograph to see whether a star is moving slightly towards or away from you as it is pulled this way and that by a planet in orbit around it. You can't see the planet, it's too far away and too faint, but you can see...
So this is the research that has allowed us to find exoplanets?
Yeah, exactly, what we call exoplanets or extrasolar planets. Yes.
And how many have we found now?
It's well over 3,000. There is a different method that's now used to detect them. That the method's called the Doppler wobble technique, the one I just mentioned, because the Doppler effect, another German scientist, this is the effect of the wavelength of the light changing slightly by the towards or away from you motion of a star. But what happens is if you've got a planet going around a star, it pulls the star this way and that, and the Doppler effect is measurable for the movement of the star itself. It's a matter of only meters per second for an object the size of Jupiter, but something the size of the Earth, it's centimeters per second. And these are tiny, tiny velocities. They're not even a walking pace. They're very, very slow, and yet you can use light to measure those things.
And so as you're saying this, I'm realising how critical technology is with this and how much information there is that we could get about our universe, but we're actually impairing this with light pollution.
That's right. Yes, that's correct. Having said that, all the world's leading observatories, and there's probably half a dozen of them that will be right at the top of the heap there in terms of the excellence of the sites that they're on. They're all protected with legislation to prevent there being undue light pollution. And the legislation simply says that if you've got development nearby within up to, well, in the case of the Siding Spring Observatory in Australia, it's up to 100 kilometres, with 200 kilometres under certain conditions. Developments within that area have to comply with certain requirements.
And that's all world observatories, all leading?
Pretty well, yeah. It varies. The major observatories on the island of La Palma, in the Canary Islands, there's great observatory there in the Northern Hemisphere, the Hawaiian ones, the Chilean ones, there are protections, which are more or less effective depending on, the local circumstances.
I'd just like to go back a little bit to talk about spectroscopy again, and specifically ask you about your role in developing multi-object spectroscopy.
I thought you'd never ask.
I know, yeah. And what that is. Please explain exactly what it does.
So this marvellous technique invented by William Huggins, effectively, the idea of using a spectroscope or a spectrograph which records the spectrum. Originally it was photographically, now it's all done electronically, to work out what's going on in the heavens. That became very much the stock in trade of astronomers during the first 70, 80 years of the 20th century, in other words, up until the 1980s. In fact, it still is, but a big change happened in the early 1980s, because in the early days, you had to make your observations one star at a time. It was the only way a telescope and the spectrograph combination could work. Then in the late 1970s, a man with this absolutely delightful name of Roger Angel, who looked at the heavens.
Doesn't that
because he was an astronomer.
Yeah. But he's not a German. So
No, he's not. He's actually a Brit, but he worked at the University of Arizona. He's retired now, still one of, American astronomy's very favourite astronomers. Roger Angel thought well outside the box in terms of how you could use technology to improve astronomy. And he got mixed up with fibre optics. Now, fibre optics were, until 1970, were essentially an entertaining diversion. What they are is strands of glass, very fine strands of glass.
This is what we now use for phones and
yes, that's right.
undersea cables.
Exactly.
Yeah.
It's actually not quite glass, it's fused silica, which is glassy material. But they're drawn into these fine strands, seldom more than 1/10 of a millimetre in diameter.
Width of a hair?
It's yes, that's about twice the width of a hair. Very, very fine. And they have the property that put light in at one end and it'll come out of the other. Now, they were known, back in the 1950s.
It's like a lava lamp.
No, lava lamps are different.
The hair ones.
Yes, that's right.
Sorry, go on. Sorry for my aside there. Yeah.
They were known back in the 1950s, these fibre optics, but it was only in 1970 that the Corning Glass Works in the United States managed to draw fibres, because that's how you make them. You start off with a block of glass and then you melt it and pull it out into these fine strands. They managed to draw fibres with extremely low losses. By that, it means that if you put light in at one end, most of it comes out at the other.
There was no disruption.
Well, it's attenuation is the technical term.
Okay.
It's a reduction in the amount of light. It's absorbed by the fibre. Before that, you put light in at one end and a tiny dribble came out of the other. But from 1970, with these what were called low-loss optical fibres, that's when they became a potential for the communications industry. And so Corning and then other...
It allows sound and light to pass through it. Does it allow any other...
No, it allows light to pass through it.
Okay.
You can put light in at one end and it will come out of the other. If you want to transmit sound through it, you've got to turn that sound signal into light.
Clever.
So that's modulating, a light source. You imprint a sound wave on it and that transmits through the fibre, comes out the other end, and you decode it and you get the sound out.
Amazing.
So that's how communications work. But astronomers, and Roger Angell in particular, he thought, well, these things are brilliant because astronomers are always jealously guarding the amount of light that they receive because it is so faint. Usually we're talking about single photons, individual particles of light. So can we use these newfangled optical fibres? And in fact, his first idea was to have many, many telescopes, smallish telescopes, all coupled together with optical fibres. So you gather the light from all these telescopes and bring it back to a single place. And you can add all the light together. On
one single object? Or on...
Yes, on one single object, that's right. But then he turned the idea on its head and realised that with one big telescope, which is looking at an area of sky, instead of just taking one star or galaxy from within that field of view, you can actually use these optical fibres to line up a fibre on many, many objects simultaneously.
So let me get this right. We have a field of sky. We have maybe a planet, or is that too close?
Yeah, we don't bother with planets for this technique. It doesn't work.
We're looking at far-off galaxies and far-off stars, and we could have 15 or 20 items in a sky, and we could be looking at all of them and getting this barcode of information from these stars
simultaneously. Because you can put a fibre on each one. And in fact, the first one I built actually had 39 optical fibres, which by the standards of the day were quite large.
And that means 39 objects?
Simultaneously. So what Roger Angell did, he got a PhD student by the name of John Hill to work on this, and they built something called Medusa, which Medusa's
the hair.
Yeah.
Lovely. Yeah.
And that had, I think, 25 fibres. And they tried it out on a telescope in Arizona at the Stewart Observatory, and it worked. It was a technique that worked really well. But then astronomers in Australia got hold of the idea, and in particular, an engineer at the Anglo-Australian Telescope by the name of Peter Gray, he worked out that you could engineer this thing in a far more effective way than Medusa. And I worked with Peter. He was working with the Anglo-Australian Telescope. I worked with a smaller telescope called the United Kingdom Schmidt Telescope, which has a very wide field of view. And together we produced kind of workable optical fibre systems for these two telescopes, which kind of took the lead in the world on this science.
Could you tell us the names of these?
Well, Peter built the, what was it called, the fibre optic coupler. So I can't remember the name, but it turned into FOCAP. That was the acronym. I built something called the Fibre Linked Array Imagery Formatter, which was FLAIR. And then FLAIR was built in the early 1980s. It was the first multi-fibre spectroscopy system that coupled the telescope to a spectrograph which was actually stationary in the dome. Now, that sounds a bit weird and esoteric, but what it meant was the spectrograph, which is a very delicate piece of equipment, was not riding around on the back of the telescope. It was fixed on the floor and was incredibly stable. And that's, so we were the first to do that. So FLAIR was the pioneer. Then I built a second version because FLAIR had certain inadequacies. The second one was the panoramic area coverage with higher efficiency, which was Panache.
So FLAIR,
Panache. Yeah. Well, what clearly came next was Finesse. Until one of my colleagues said, Finesse stands for fails to interest nearly everyone, save spectrograph engineers. So we actually called it Flare 2 instead.
Flare 2.
But that then evolved to a robotic system with this more boring name of 60F, with 150 fibres. That was commissioned in 2001. And now we're building an amazing machine called Taipan, which uses things called starbugs. So each optical fibre... 60F had a single robot to move the fibres around, but with Taipan, each fibre, there'll be 300 in the end, has its own micro-robot positioning them around. Meanwhile, the Anglo-Australian Telescope back in 1996 built something called 2DF. 2DF stands for 2-degree field. That's the amount of sky the thing sees, and 2DF had 400 fibres. But I have to tell you, the AAO, which now stands for Australian Astronomical Optics, it used to be the Australian Astronomical Observatory, AAO is building a system with more than 400 fibres for a telescope in Europe, a European telescope.
Australia cuts its way up, doesn't it? It really does punch above its weight with regards to its technology and development.
Well, that's right. That's why Australian astronomers have had such given we're a small country, because we have this equipment that, we build it probably more effectively than anywhere else. Somebody said we should call ourselves Fibres Are Us, because that's what we do. We do optical fibres. The technique is in use around the world, but many of the ones that are used elsewhere are ones that have been built by the AAO in Australia. Yeah.
Fantastic. So just keeping on the technology theme here, I heard Margaret Atwood, of all people, she's the person that wrote The Maiden's Tale?
Handmaidens,
that's right. And the comment was that all technologies have got a good use, a bad use, and a stupid use that we never considered. And I'm just thinking about light, and particularly with astronomy, what would you think the good, the bad, and the stupid uses are?
Well, look, for optical astronomers, that's visible light astronomers, and I'm not now talking about radio astronomers or X-ray astronomers, because these are all different disciplines, although we're all looking at the same things.
In a different way.
And often those results all piece together. Optical astronomers, their stock in trade is light, so they are obsessed with light, and more especially obsessed with actually getting the very best information from light. So the good is what we learn from the sky by sifting light through the spectrographs and other types of instruments.
Natural light from the sky.
Yeah. The bad is light pollution, of course. So that's when light, which is being used for a completely innocent purpose, but gets out of hand, in particularly in the light plumes of cities. And really it goes back to the early 20th century, when councils put in lights with really no regard to what that was doing to the night sky, because we simply never thought about it. It was becoming a problem by the time of the Second World War. It's really interesting.
As early as that?
Yeah, in Los Angeles, which is very near the Mount Wilson Observatory. In fact, you can see Los Angeles from Mount Wilson, where at the time the biggest telescope in the world was. During the Second World War, Los Angeles had blackouts in order to mitigate the possibility of invasion. And during that time, huge astronomical discoveries were made because the night sky could be seen properly from Mount Wilson again. So it was inadvertent. So that's the bad side.
Just on that, I've attended some conferences in the UK, and one of the issues that they have when they talk about trying to mitigate light pollution in the UK is that if you start talking to people, particularly in that sort of generation, about turning off street lights and lights, they feel like it's taking them back to the war.
The war, that's right. Just like the blackout. Yeah. We had to do that in blackout days. Yeah. Yes, I know. I remember people saying all that. And that's true. But it's not a blackout. I mean, what we're talking about now is good lighting, because there's been huge progress in the last 20 years with understanding the ills of light pollution, and it's not just for astronomers, where the least important in many ways of the consequences of bad lighting.
Again, when I talk to groups about light pollution, I haven't often, but I have been asked by people, well, why do we have to keep the lights down for the astronomers when you've got a whole heaven of stars, why can't they just study the star to the left or the brightest star or whatever? And I think in some ways we lost that argument when we talked 30 years ago when the International Dark Sky Association started, and it was astronomers saying, oh, we're losing our night sky. That story was lost on the general public. They didn't understand the information that you're getting about our heavens.
But that's probably true. They think, most people think an astronomer is a middle-aged bald man with a white coat who's got a long spindly telescope and just spends his nights looking through it. And nothing could be further from the truth. It's all about, well-directed scientific problems. We're trying to understand the universe because that understanding might actually turn out to be really useful to us one day. And it's conducted in a very progressive way. It's not just looking for the sake of looking. We're studying, and of course, the other great thing is that it's no longer a bald, middle-aged man.
It's much more diverse.
We are far more diverse than that. Yeah.
So that's the good and the bad.
Yeah. What's the quirky?
What about the stupid use of technology that maybe has come through astronomy, through light, and I know of things. You talked about the Doppler effect, isn't?
Yeah. So I actually, you could almost lump the fibre optics work that I was talking about into it's certainly quirky because in 1970 nobody had thought in this direction. It was Roger Angell towards the end of the 1970s was thinking outside the box as to what you could use these technologies for. And I do remember when I started working on this in 1982, building FLARE, the first fibre optic system for the Schmidt telescope, one of my colleagues called it Watson's folly because nobody believed that it would do anything useful, that it would just, it was just be quirky. It's a bit like... back in the post-war period, the then director of the Mount Stromlo Observatory, which was Australia's national observatory at that time, at Mount Stromlo in Canberra, the Commonwealth Observatory, Sir Richard Woolley, somebody said to him, so where do you think radio astronomy will be in 10 years' time? And he said, forgotten. And I think people thought that about the fibre optics work. Where do you think fibre optics will be in 10 years' time? Forgotten. And it's not.
And yet it's now going to be used on the biggest telescopes.
It is already being used on the biggest telescopes in the world. It absolutely revolutionised the science because what it lets you do, as I said, we didn't carry through the conversation that it lets you look at many objects at a time, 400 on the AAT. It'll be 4,000 on the Vista telescope, which is in Chile, operated by the Europeans. That then allows you to gather enormous data sets of the most intimate statistics of stars and galaxies and quasars, all these objects in the wider universe. And by doing that, you can... First of all, you can do population census studies. You can look at the trends. You can start discovering a lot about the evolution of the universe. It's how we know, for example, that the Big Bang model of the origin of the universe, how that is almost certainly the correct model, because we can see its imprint all over the millions of galaxies that we now have three-dimensional positions for, thanks to the fibre optic technique. So it's kind of revolutionised that study, but it also shows up the real oddballs. So if you're looking at, 4,000 stars at a time, you're going to find things that are very, very unusual. And they're the ones that point the way to things like new physics, the understanding that relativity and quantum theory might not be all that there is. These are things that they're the best models of reality we've got. But we still find gaps in them. And what we're looking for is what might be hidden underneath, which could lead to all kinds of things like teleportation, time travel, and all that great stuff.
And it actually leads me into the other question that I had is a real basic one, but what is the speed of light?
The speed of light is...
talking about Einstein and right. all that we know from him.
So, so going back to 1905, when Einstein published his special theory of relativity, which, these are gobbledygook words, but that's a theory of the way objects move. and it sort of built on what Newton wrote in 1687 in his book Principia. The Principia. He wrote his laws of motion, which are fine and work well until you get near the speed of light. The speed of light was already well known at that time, 300,000 kilometres per second.
How was it known?
Actually, it was first measured by a Danish astronomer in 1687 by looking at the moons of Jupiter, a man called Rømer. He worked, I think, in Copenhagen, studied the moons of Jupiter and realised that the way they behaved, as he could see them in the sky, meant that there was a time lag in the travel time of the light from the backside of Jupiter to the front side of Jupiter. And he analysed all that, and he got a cracking good answer for the speed of light. There was actually French physicists in the late 19th century who really kind of tied it down. But what was curious, and this is what fed into Einstein's thinking, was that everybody expected the speed of light would be something variable. So that if you think about the speed of sound here on Earth, the speed of sound is carried through air, and if you're on a moving object like a car, and the speed of sound changes for you because it's
So if you're stationary and you have a car go past you, you can hear.
Well, that's the Doppler effect. Actually, that's going back to what we were talking about earlier. But everybody expected that, you know, if you were looking at a source of light, and that light is reaching you at 300,000 kilometres per second. If you're stationary, yeah, that's fine. But the thinking was, if in fact you're moving towards that light at 100,000 kilometres per second, then you should see its speed as being less than or more than what it actually was. It turns out that the speed of light is fixed in a vacuum. Doesn't matter how you're moving, how the light source is moving, it is always 300,000 kilometres per second. And once you realise that was actually confirmed by two Americans, Michelson and Morley, in the 1880s, that the speed of light is invariant. And Einstein fed that into his work and realised that actually the speed of light is almost mystical. Because space can vary. Space can change its shape depending on your motion, and time can change depending on your motion. But the speed of light doesn't. It's the thing that's immutable.
Constant.
It's an absolute constant. Yeah. There is a small group of scientists, one of whom is based here in Australia, a man called John Webb, who's nearly always somewhere else in the world, which is why he's called the World Wide Web. John Webb is, he believes he has evidence that the speed of light was different in the early universe. Looking back 13.6 billion years. The beginning of the universe was 13.8 billion years ago, to the best of our knowledge. And he looks back nearly all that way and thinks he can see evidence that the speed of light has changed. It's a very speculative result, and not many astronomers believe him, but John Webb is convinced of that, from the University of New South Wales.
Oh, well, we'll keep an eye on that to see how it progresses.
Yep.
Yeah. So, Fred, when was the last time you looked at the night sky?
Last night.
Did you?
Yep. I went out and looked at the stars and thought, yeah, there's a bit of cirrus around. It's not a brilliant night. Yeah,
So when was the best time you looked at what's the most memorable experience you've had in the nighttime environment?
It's because my life has been in astronomy, and it goes back now a long way. There are many that I could talk about. One of them was in the early 2000s, 2006, 2007. Late in 2006, a colleague of mine, Robert McNaught, at Siding Spring, discovered a comet. That was his job. He discovered comets. But this one turned out to be incredibly bright. And in the early months of 2007, it was just dazzling in the western evening sky. And where I lived at that time was totally free from light pollution. Does a comet just come once, or do you... That particular one does, yeah. Not all of them do. Some go around the sun. Many of them are in orbit around the sun. But comets actually come from the depths of the solar system. In fact, almost halfway to the next nearest star, there's a sort of shell of these icy objects called the Oort cloud, named after a man called Jan Oort, who was a Dutch astronomer in the mid-20th century. He said there must be a cloud of icy objects out there which fall inwards towards the solar system, and when they get near the sun, the ice evaporates and they become luminous.
And he was right.
Yeah, he was right. And that's how we know about comets. So Comet McNaught was one of these that came out of the blue. Rob McNaught detected it when it was quite faint, but it turned out to be probably the most spectacular comet of the century so far. And it may be the most spectacular for the whole century. It was just
might be the most spectacular one you see.
Yeah.
Yeah.
So that's one. But I've got a very fond memory of a night which would have been in the early 1980s. And it was when I was building the first of these fibre optic systems, the flare thing that I mentioned. That was a device that, as I said, used optical fibres to pick the light of stars from the focus of the telescope. And the fibres brought them out of the telescope to basically a little thing that just lined them all up in a straight line. Now, this straight line was about half an inch long, 13 millimetres or something like that. But it had 39 optical fibres in it, each of them about a tenth of a millimetre in diameter. And it was a crystal clear night, and I'd got the telescope all set up and thought this was right at the beginning of these experiments. And I picked up this little fibre unit from the floor, which I knew had the light of stars coming down it. And I looked in the end, and I just saw a line of little lights, all different colours, because stars are different colours. The colour is dependent on the temperature. And it was magical.
So you were standing there with
holding
light.
starlight in my hand, with these 39 fibres lit up, shining away. And it was the real reason why it was a buzz is because it's actually quite hard to get light down fibres. It has to be done very, very precisely. And at that point, I knew I could do it, and I knew the instrument was going to work, and it did.
Amazing. Amazing. So just to finish up, I'd like to ask you, if you had your soapbox and 3 minutes of time,
yes,
what do you want people to know about light and light pollution?
Okay, so this is where I become, an advocate. It's not quite activism. It's very gentle activism. What do we want? What do we want? Moderate change. When do we want it? In due course. So that's my soapbox. And what I would tell people is that is ask them to think about where their light is going. Light basically goes on forever. I mean, it does dwindle away to very faint levels. But if you're sending a beam of light upwards into the sky, what's it going to do? It's going to light up the molecules of the atmosphere and spoil that view of the sky for somebody else. And it's a death by 1,000 cuts. So individually, our contribution to light pollution is very low. But collectively, when you've got a city like Sydney with more than 4 million people living there, nobody thinks about where the light is going, then you've got a city in which it is impossible to see the stars. So it's just to think about lighting up only what you want to light up, keep the light below the horizontal plane so none of it's going upwards into the sky. And there's a subtlety here. We now know that light that is rich in blue, and that's really that dazzling white light that we're getting used to from
bright white light
emission diodes, light emitting diodes, LEDs. That light we now know is not good for human health at night because it fools our circadian rhythms into thinking it's still daylight, and that screws up everything. So think about light. That's the answer.
Thanks for your time.
It's a great pleasure. Anytime.
Thank you. Well, that's it for Dark Sky Conversations this week. We hope you enjoyed it. We'd love to hear your feedback, thoughts, or if you've got any questions about light pollution. So send us an email, podcast@darkskytraveller.com.au, or Instagram us at DarkSkyOz. Please subscribe to our podcast at iTunes, Stitcher, Spotify, or wherever you get your podcasts from. And while you're there, give us a review. Thanks again. That's it for me this week. Until next week, lights out.